Imagine peering into the inky blackness, reaching across trillions of miles to touch the faintest whisper of light from another star. Now, picture trying to decipher a message encoded in that whisper, a message 1,000,000 to 1,000,000,000 times fainter than the star itself. Sounds impossible, right? Well, hold on to your cosmic hats, because NASA scientists have just pulled off a mind-bending feat of astronomical detective work that's sending shockwaves through the scientific community. Breaking news from the very edge of space exploration reveals a stunning breakthrough. The seemingly insurmountable mountain of data gathered by the James Webb Space Telescope from our nearest potentially habitable exoplanet, Proxima B, has finally yielded its long-held secrets. And the key to unlocking these secrets? Nothing short of revolutionary, advanced quantum AI processing. These cutting-edge algorithms have managed to sift through Webb's complex readings in ways that traditional supercomputers could only dream of, revealing patterns and nuances that were previously invisible, hidden in plain sight within the vast ocean of data. For years, Proxima B has captivated the imaginations of astronomers worldwide. Orbiting Proxima Centauri, our closest stellar neighbor a mere 4.24 light-years away, it tantalizingly sits within the theoretical habitable zone of its star, the region where temperatures could potentially allow for liquid water to exist on its surface. This proximity makes it a prime candidate in our ongoing quest to find life beyond Earth. The Webb telescope, with its unprecedented infrared sensitivity and spectral resolution, was specifically designed to scrutinize the atmospheres of such distant worlds, hoping to detect the telltale signs of life, biosignatures. However, the sheer volume and complexity of the data streaming back from Webb proved to be a significant bottleneck. Traditional supercomputers, powerful as they are, simply couldn't untangle the intricate web of signals and noise to extract the subtle information needed for a comprehensive understanding of Proxima B's atmosphere and surface. The faint light filtering through the exoplanet's atmosphere as it passed in front of its star, a transit, contained a wealth of information about its chemical composition, but deciphering that information was like trying to hear a single raindrop in a hurricane. But now, everything has changed. The advent of advanced quantum AI algorithms has provided scientists with an entirely new lens through which to examine this treasure trove of data. These algorithms, leveraging the mind-boggling principles of quantum mechanics, possess the ability to process information in fundamentally different and far more efficient ways than classical computers. They can explore multiple possibilities simultaneously, identify subtle correlations across vast datasets, and essentially see patterns that would remain buried in the noise for even the most powerful traditional systems. This isn't just an incremental improvement. It's a paradigm shift in how we analyze astronomical data, and its first major triumph lies in the revelations about Proxima B. What these quantum algorithms have unearthed is nothing short of astonishing, fundamentally altering our understanding of this enigmatic world orbiting our closest stellar neighbor. The initial findings hint at something so unexpected that even the most optimistic researchers hadn't dared to dream of seeing it within the data. But before we dive into the groundbreaking discoveries made possible by this quantum leap in data processing, let's take a moment to appreciate why Proxima B has held such a strong grip on the scientific community since its discovery in 2016. Its very existence so close to our own solar system presented an unparalleled opportunity to study a potentially habitable world. Unlike exoplanets located hundreds or thousands of light-years away, Proxima B offers the tantalizing prospect of more detailed future investigations. Imagine, one day, the possibility of sending advanced probes to directly study this world. This proximity fuels our hopes in the search for life beyond Earth and makes every piece of information we can glean from it incredibly valuable. After years of dedicated study, sifting through data that once seemed impenetrable, NASA scientists have finally struck gold, uncovering something truly remarkable hidden within the James Webb Space Telescope's observations of Proxima B. The first wow moment came with the detection of unusual spectroscopic signatures in Proxima B's atmosphere. Specifically, the quantum AI system identified an unexpectedly high concentration of methane that doesn't just sit at a constant level. It fluctuates in a regular, cyclical pattern. Now, methane itself isn't necessarily a definitive sign of life. It can be produced by geological processes as well. However, the key here is the regular variation of its concentration. These subtle shifts were completely masked by the background noise in the raw data, like faint whispers drowned out by a loud crowd. It was only the advanced noise-canceling capabilities and pattern recognition prowess of the quantum AI that managed to clean up the signal and reveal this intriguing oscillation. This discovery is profoundly significant because on our own planet, Earth, methane exhibiting this kind of predictable, recurring variation is often strongly linked to biological processes. Think about it. Cows produce vast amounts of methane through their digestion, and seasonal changes in plant life can also influence atmospheric methane levels. While we can't definitively say that the methane fluctuations on Proxima B are biological in origin, the similarity to Earth's patterns raises a tantalizing question. Could this be the first faint whisper of life beyond our solar system? Traditional computer analysis, constrained by its linear, step-by-step approach, simply couldn't discern these delicate temporal changes. The quantum AI, however, with its ability to analyze the entire dataset simultaneously and identify complex correlations across multiple data points, like how the methane levels correlate with other atmospheric components over time, was able to pull this subtle signal out of the overwhelming background noise. The difference is stark. Before the quantum AI processing, the Webb data regarding Proxima B's atmosphere appeared as a chaotic jumble of random fluctuations, offering no clear, discernible patterns. After the quantum AI worked its magic, clear, cyclical patterns emerged, painting a completely different picture. These patterns strongly suggest either seasonal changes occurring on the planet, driven by its orbit around Proxima Centauri, or potentially something far more intriguing about Proxima B's fundamental atmospheric chemistry, perhaps even the influence of biological activity. If you're as captivated by these groundbreaking revelations as we are, make sure you hit that subscribe button and ring the notification bell. We're committed to bringing you the very latest discoveries from the frontiers of space exploration, often before anyone else. Don't miss out on the next thrilling chapter of our cosmic journey. To truly grasp the profound implications of this methane discovery, we reached out to a true pioneer in the field of exoplanet atmospheric research, Dr. Sarah Seager, the renowned MIT astrophysicist. Dr. Seager has dedicated her career to developing the very methods we use to search for biosignatures on distant worlds. Her insights are invaluable in understanding the significance of these new findings. According to Dr. Seager, the development and application of advanced computational methods, particularly quantum-inspired algorithms, are revolutionizing the way we analyze the vast amounts of data collected from exoplanets. The James Webb Space Telescope is an absolute marvel, gathering information at an unprecedented level of detail and resolution. However, she emphasizes that extracting meaningful patterns and potential biosignatures from this massive and complex data requires computational power that traditional systems simply don't possess. These new quantum-enhanced processing techniques are like upgrading from a magnifying glass to an incredibly powerful microscope, allowing us to see signals that would otherwise remain completely buried beneath the layers of noise. Dr. Seager has spent decades meticulously developing the theoretical frameworks and methodologies for identifying potential biosignatures, chemical fingerprints of life, on exoplanets. This deep expertise makes her assessment of these new findings from Proxima B particularly significant and highly respected within the global scientific community. Her validation adds a crucial layer of credibility and excitement to this initial discovery. But hold on, because the story doesn't end there. What researchers discovered next in the Webb data, thanks to the relentless work of the quantum AI, is even more mind-blowing than the fluctuating methane levels. What do you think these unusual atmospheric signatures and their cyclical behavior could indicate about Proxima B? Let us know your theories and speculations in the comments section below before we reveal what scientists currently believe might be happening on this fascinating world. Your ideas could be more insightful than you think. After meticulously analyzing thousands upon thousands of spectroscopic readings gathered from the James Webb Space Telescope's extended observations of Proxima B, the quantum AI system delivered yet another truly remarkable discovery, the second wow moment of this incredible story. It identified clear and consistent seasonal variations in the exoplanet's atmospheric composition, variations that follow a predictable and repeating cycle. Specifically, the data revealed a distinct pattern of carbon dioxide, CO2 levels that rise and fall in a synchronized manner over what appears to be Proxima B's year. A surprisingly short cycle lasting just 11.2 Earth days, which is the time it takes for the planet to complete one orbit around its host star, Proxima Centauri. This discovery has profound implications for our understanding of Proxima B's climate dynamics and overall environment. One of the long-standing questions about tidally locked planets like Proxima B, where one side perpetually faces its star and the other remains in permanent darkness, was whether they could effectively distribute heat and maintain a stable atmosphere. The concern was that the extreme temperature difference between the day and night sides would create atmospheric collapse on the dark side, rendering the planet uninhabitable. However, the cyclical variations in CO2 levels strongly suggest that Proxima B's atmosphere is far more dynamic than previously imagined. It indicates a global circulation pattern, where gases and heat are being transported from the intensely irradiated day side to the frigid night side, and vice versa. This efficient atmospheric circulation effectively homogenizes temperatures across the planet to a greater extent than initial models predicted, potentially mitigating the extreme temperature gradients. This unexpected atmospheric dynamism is incredibly encouraging because it suggests that Proxima B might possess more moderate temperature variations across its surface than scientists initially believed. This, in turn, could significantly widen the planet's habitable zone, the regions where liquid water could persist on the surface. The quantum AI processing was absolutely crucial in uncovering these subtle yet significant patterns. It achieved this by meticulously correlating minute changes in the absorption spectra across multiple wavelengths of light over extended periods. When viewed individually, these spectral shifts might appear random and insignificant. However, when the quantum AI system mapped these vast amounts of data together, it revealed clear and consistent cyclical shifts in CO2 concentration that corresponded precisely with the planet's relatively rapid 11.2-day orbit around Proxima Centauri. This ability to see the bigger picture by identifying intricate connections within a massive, multi-dimensional dataset is a hallmark of quantum-enhanced AI. Most exciting for researchers is what these atmospheric cycles strongly suggest about Proxima B's potential to support liquid water, a key ingredient for life as we know it. The observed patterns of rising and falling CO2 levels, in conjunction with the inferred global atmospheric circulation, indicate temperature variations that would likely allow for both evaporation on the warmer day side and precipitation, potentially on the cooler night side or along the terminator region, the boundary between day and night. This points towards the possibility of a rudimentary water cycle operating on Proxima B, where water could exist in liquid form in certain regions and at certain times. This dramatically increases the likelihood that at least some portions of Proxima B's surface could maintain conditions suitable for liquid water to exist, even if not across the entire planet. While these seasonal variations are already a fascinating and significant discovery, the third major revelation unlocked by the quantum AI processing of Webb's data is arguably even more puzzling and captivating. The third wow moment that truly challenges our existing understanding of this alien world. The third major revelation, the third consecutive wow, came when scientists directed the powerful quantum AI system to meticulously analyze the James Webb Space Telescope's thermal imaging data of Proxima B. While the spectroscopic data provided insights into the atmospheric composition and dynamics, the thermal imaging offered a direct look at the planet's surface temperature distribution. The enhanced processing capabilities of the quantum AI unveiled something completely unexpected and utterly baffling: distinct thermal hotspots distributed across Proxima B's surface. What was particularly intriguing was that these hotspots were primarily concentrated along what appears to be the terminator line, the twilight zone that separates the perpetually sunlit day side from the eternally dark night side of this tidally locked world. What makes this discovery so remarkable and challenging to our current understanding is that these localized regions of elevated temperature simply don't match the predictions generated by any existing climate models for tidally locked exoplanets. Traditional analysis of the thermal data, relying on classical computing methods, had only revealed a relatively smooth gradient of temperature change, gradually decreasing from the hot day side to the cold night side, as one would intuitively expect. There was no indication of these discrete, warmer patches. However, with the quantum AI's ability to process the vast amounts of multi-wavelength infrared data simultaneously and filter out the significant interference from Proxima Centauri's stellar activity, researchers could now clearly discern these localized regions maintaining temperatures up to 15 degrees Celsius, around 27 degrees Fahrenheit, warmer than their surrounding areas. These thermal anomalies appear as thermal oases, dotting the planet's twilight zone, defying our expectations of a simple temperature gradient. The quantum AI was absolutely essential in identifying these unusual thermal patterns. Its capacity to process multi-wavelength infrared data concurrently, while also effectively filtering out the noise generated by Proxima Centauri's inherent stellar activity, which can often mask faint signals from orbiting planets, is a computational task that would take conventional supercomputing systems months, if not years, to complete. This ability to disentangle the faint planetary signals from the overwhelming stellar background is a game-changer in exoplanet research. Faced with these perplexing thermal anomalies, scientists have begun to propose several competing hypotheses to explain their existence. Dr. Guillem Anglada Escudé and Dr. Cristina Rodriguez-Lopez, who led the team that first discovered Proxima B back in 2016, suggest that these hotspots could be caused by significant geological activity on the planet. Perhaps there are active volcanic regions scattered along the terminator line, releasing substantial amounts of heat from Proxima B's interior. This would be a fascinating discovery in itself, indicating a geologically active world. Another compelling theory, proposed by the esteemed planetary scientist Dr. Victoria Meadows, points to the possibility of varying thermal inertia across different types of surface materials present on Proxima B. Certain materials might have the property of retaining and slowly releasing heat more effectively than the surrounding terrain. For example, A large area of dark, rocky material might absorb significant heat during the day, and then radiate it back out more slowly as it rotates into the twilight zone, creating a localized warm spot. Perhaps most intriguing, especially in the context of potential habitability, is the hypothesis put forth by Dr. Abel Mendes, the director of the Planetary Habitability Laboratory at the University of Puerto Rico at Arecibo. He speculates that these thermal patterns could indicate the presence of large bodies of liquid water, such as oceans or large lakes, situated along the terminator line. Water has a high heat capacity, meaning it can absorb and store large amounts of thermal energy and release it slowly, acting as natural thermal reservoirs. If this hypothesis proves correct, it would dramatically increase Proxima B's potential for habitability, as liquid water is considered a fundamental prerequisite for life as we know it. However, the truth behind these enigmatic thermal hotspots remains a mystery, and further investigation is crucial to unravel their origin. But the string of incredible discoveries didn't end there. The most extraordinary finding, the one that truly sent ripples of excitement throughout the scientific community, emerged when scientists applied the quantum AI's unparalleled analytical power to Proxima B's electromagnetic data. The most unexpected and arguably most significant breakthrough, the fourth and perhaps most pivotal wow factor in this incredible saga, came when the quantum AI analysis shifted its focus to Proxima B's electromagnetic signature. For years, a major concern regarding the habitability of planets orbiting red dwarf stars like Proxima Centauri has been the intense stellar activity they exhibit. These stars are known for frequently erupting with powerful flares, spewing out vast amounts of high-energy radiation and charged particles known as stellar winds. A long-standing worry about Proxima B, due to its relatively close orbit and the fact that it is likely tidally locked, was that it might not possess a strong enough global magnetic field. A robust magnetic field is crucial for a planet because it acts as a protective shield, deflecting these harmful stellar winds and preventing them from stripping away the planet's atmosphere over time. Without this atmospheric protection, any potential for surface liquid water or life, as we know it, would be virtually impossible. However, the new analysis conducted by the quantum AI revealed something truly remarkable and incredibly encouraging. Compelling evidence of a substantial planetary magnetic field surrounding Proxima B. What's even more surprising is that this field appears to be potentially strong enough to effectively deflect the energetic stellar winds emanating from Proxima Centauri, thus providing crucial protection for the planet's precious atmosphere. The quantum AI achieved this groundbreaking detection by identifying incredibly subtle polarization patterns in the light that filters through Proxima B's atmosphere as it transits its star. These minute changes in the polarization of light are indicative of interactions occurring within a magnetosphere, the region of space dominated by a planet's magnetic field. Detecting these faint signals amidst the noise of stellar activity required the extraordinary sensitivity and analytical capabilities of the quantum AI. Dr. Natalie Batalha, a renowned astrophysicist who served as the mission scientist for NASA's highly successful Kepler mission, which discovered thousands of exoplanets, eloquently explains the profound significance of this magnetic field discovery. She emphasizes that a robust magnetic field is considered absolutely essential for the long-term habitability of planets orbiting volatile M-dwarf stars like Proxima Centauri. These stars are notorious for their frequent and powerful flares, which can unleash torrents of radiation that would otherwise relentlessly erode a planet's atmosphere, leaving it barren and lifeless. Finding clear evidence of a magnetic shield around Proxima B dramatically improves its prospects as a potentially habitable world, addressing one of the most critical challenges previously identified. However, while the detection of a magnetic field is undoubtedly a major step forward, not all scientists share the same level of unrestrained optimism. Dr. Feng Tian, a respected atmospheric scientist at the Chinese Academy of Sciences, offers a more cautious perspective. He acknowledges the significance of the magnetic field discovery, but reminds us that the proximity of Proxima B to its host star still presents extreme challenges. As he points out, even with magnetic protection, Proxima B likely receives significantly more high-energy radiation, such as X-rays and ultraviolet radiation, than Earth does from our Sun, perhaps as much as 400 times more. Therefore, he argues that while a magnetic field is a vital piece of the puzzle, it would need to be extraordinarily strong and effective to maintain conditions truly suitable for complex life over extended periods. Dr. Lisa Kaltenegger, the director of the Carl Sagan Institute at Cornell University, takes a more measured and nuanced position. She agrees that the detection of a magnetic field around Proxima B opens up exciting new possibilities and significantly boosts its habitability potential. However, she also cautions against anthropocentric thinking, reminding us that life on Earth has demonstrated an incredible ability to adapt and thrive in a vast range of extreme environments, from the crushing pressures and darkness of deep-sea hydrothermal vents to the frigid, seemingly inhospitable conditions of Antarctic ice. Therefore, even if the conditions on Proxima B aren't perfectly aligned with what we currently consider ideal for complex life as we know it, we shouldn't underestimate the potential for evolutionary adaptation and the possibility of life forms that are fundamentally different from those we are familiar with. Dr. Kaltenegger suggests that we should always be prepared for the unexpected when it comes to the diversity of life in the universe. Building on this thought, some researchers have gone even further, actively speculating whether this newly discovered magnetic protection, combined with the previously revealed thermal patterns and atmospheric cycling, could have provided enough stability and shielding over billions of years for life to potentially arise and even evolve on Proxima B, the combined picture emerging from the quantum AI analysis. Protection from stellar radiation, localized thermal oases, and a dynamic atmosphere capable of distributing heat and potentially supporting a water cycle, paints a far more promising and intriguing portrait of Proxima B than we have ever had before. However, the scientific debate continues, with researchers diligently working to understand the true implications of these groundbreaking findings for the ultimate question: is our nearest exoplanetary neighbor a potential abode for life? What's undeniably clear is that our fundamental understanding of this enigmatic world has been profoundly and irrevocably transformed by these remarkable new insights, all thanks to the power of quantum-enhanced data analysis. Now that we've journeyed through these incredible and interconnected discoveries, let's take a closer look at the revolutionary technology that made them possible: quantum AI. The term quantum AI refers to a fascinating and rapidly evolving hybrid approach that strategically applies the unique principles of quantum computing to significantly enhance the capabilities of artificial intelligence algorithms. To understand the power of quantum AI, it's helpful to first grasp the fundamental difference between classical computing and quantum computing. Traditional computers, the ones that power our laptops and smartphones, process information using bits. Each bit can exist in one of two states, either a 0 or a 1, representing off or on. Quantum computers, on the other hand, utilize quantum bits or qubits. What makes qubits revolutionary is their ability to exist in multiple states simultaneously through a mind-bending quantum mechanical phenomenon called superposition. Imagine a coin spinning in the air. It's neither heads nor tails until it lands. Similarly, a qubit can be both 0 and 1 at the same time, existing in a probabilistic blend of these states. Furthermore, Qubits can also exhibit another quantum phenomenon called entanglement, where two or more qubits become linked together in such a way that they share the same fate, regardless of the physical distance separating them. Measuring the state of one entangled qubit instantaneously influences the state of the others. This fundamental difference in how information is processed allows quantum AI systems to tackle problems that are intractable for even the most powerful classical supercomputers. When analyzing the immense and incredibly complex datasets generated by the James Webb Space Telescope's observations of Proxima B, quantum AI systems could leverage superposition to explore a vast number of potential pattern correlations across different wavelengths of light and across extended time periods all at once, rather than having to laboriously check each possibility sequentially, one after the other. This parallel processing capability provides an exponential speedup for certain types of computational tasks, making it possible to identify subtle and hidden relationships within the data that would remain buried for classical systems. Dr. John Preskill, a renowned theoretical physicist at Caltech and a pioneering figure in the field of quantum computing, eloquently explains the advantage. Quantum algorithms excel at identifying hidden correlations and subtle patterns within extremely complex datasets. Traditional computing methods might take months, years, or even an eternity to detect certain faint signals, whereas quantum-enhanced systems can potentially identify these crucial features in a matter of days or even hours. This dramatic increase in analytical speed and capability is precisely what allowed scientists to unlock the secrets hidden within Webb's data from Proxima B. The James Webb Space Telescope itself is a technological marvel, generating these massive datasets through its suite of highly specialized scientific instruments. Its near-infrared spectrograph, NIRSpec, is a key player in this story. NIRSpec can essentially detect the unique chemical fingerprints of various elements and compounds present in Proxima B's atmosphere by meticulously analyzing how different wavelengths of infrared light are absorbed or transmitted as they pass through the planet's atmospheric layers during its transits across the face of its star. Each molecule absorbs light at specific wavelengths, creating a unique absorption spectrum that acts like a barcode, revealing the atmospheric composition. Meanwhile, Webb's mid-infrared instrument, MIRI, provides crucial thermal imaging capabilities. It was MIRI that detected those intriguing and unexpected thermal hotspots on Proxima B's surface. This instrument is incredibly sensitive, capable of perceiving minute temperature differences as small as 0.1 degrees Celsius from a staggering distance of 4.24 light-years, a truly stunning technological achievement. Together, these sophisticated instruments generate terabytes upon terabytes of raw data from each observation of Proxima B before scientists can even begin to look for meaningful patterns. This raw data must undergo a rigorous and complex filtering process to remove various sources of interference, including the faint glow of cosmic background radiation, scattered light from dust within our own solar system, and most significantly, the overwhelming brightness of Proxima Centauri itself. This crucial filtering process presents an enormous computational challenge, one that routinely pushed traditional supercomputers to their absolute limits. Previous attempts to study Proxima B before the advent of Webb and quantum AI faced significant hurdles. The European Southern Observatory's espresso spectrograph was instrumental in first confirming the planet's existence and providing basic parameters like its mass and orbital period back in 2016. The Hubble Space Telescope, a venerable workhorse of astronomical discovery, also attempted to analyze Proxima B's atmosphere. However, Hubble lacked the crucial infrared sensitivity needed to effectively penetrate the planet's atmospheric layers and obtain the detailed spectroscopic data required to determine its composition. Dr. Nicol Lewis, a highly respected astrophysicist at Cornell University and a dedicated scientist working on the James Webb Space Telescope mission, aptly describes the challenges faced before Webb and quantum AI. Before Webb, trying to study Proxima B's atmosphere was akin to trying to see a tiny firefly flickering next to an incredibly bright spotlight from miles and miles away. Webb's unprecedented infrared sensitivity and exceptional precision finally provided us with the data we desperately needed. But we quickly realized that we also required equally advanced computational methods to truly make sense of it. The quantum AI system approached this daunting analytical challenge in a fundamentally different and more holistic way than traditional methods. Instead of analyzing each individual data stream from different wavelengths or different instruments, in isolation, it created a comprehensive, multidimensional model that incorporated all available information simultaneously, including data from different wavelengths, temporal variations, and even spatial information gleaned from the thermal imaging. This integrated, holistic approach allowed the quantum AI to identify subtle but crucial correlations between seemingly unrelated measurements, revealing the hidden patterns that conventional step-by-step analysis simply missed entirely. For instance, when examining the spectroscopic data for the telltale signs of methane signatures, traditional analysis would typically focus on identifying specific absorption features at a predefined set of wavelengths known to be associated with methane. The quantum AI system, however, went far beyond this. It examined how the intensity and shape of these potential methane absorption features changed not only over time, but also in relation to the behavior of dozens of other atmospheric components detected in the same dataset. This comprehensive, cross-referential analysis is what allowed it to uncover the cyclical patterns in methane concentration that strongly suggest potential seasonal variations or even biological activity. This is the key reason why previous analyses of the very same Webb data, relying on classical computing methods, had failed to detect these crucial discoveries. The patterns were always present within the complex web of data, but conventional computing systems simply lacked the ability to efficiently process the intricate, multidimensional relationships and extract these faint signals from the dominant noise. The suite of discoveries we've explored today, all made possible by the groundbreaking application of quantum AI to the James Webb Space Telescope's observations, collectively represent a quantum leap in our understanding of Proxima B, from the unexpected fluctuations in atmospheric methane and the clear seasonal variations in its overall atmospheric composition, to the baffling thermal hotspots dotting its terminator line and the encouraging evidence of a protective global magnetic field. Each individual finding dramatically reshapes our previous picture of our nearest exoplanetary neighbor. When considered together, these remarkable revelations paint a picture of Proxima B as a world that is far more dynamic, complex, and potentially hospitable than scientists had previously envisioned. The regular atmospheric cycles hint at a mechanism for distributing heat and potentially supporting a water cycle. The enigmatic thermal oases in the twilight zone raise the tantalizing possibility of localized regions with more moderate temperatures, perhaps even hosting liquid water. And the welcome discovery of a planetary magnetic field offers crucial protection from the harsh stellar radiation emitted by Proxima Centauri, potentially allowing an atmosphere to persist over long timescales. These combined factors significantly enhance the likelihood that at least some regions on Proxima B could harbor liquid water and perhaps even support simple forms of life. The possibility, once considered remote due to the challenges posed by red dwarf stars and tidally locked planets, can no longer be confidently ruled out. In light of these paradigm-shifting findings, NASA has already announced an extended and highly focused observation campaign dedicated exclusively to Proxima B. The space agency has allocated an additional 200 precious hours of James Webb Space Telescope time over the next 6 months, specifically for further in-depth study of this intriguing world. This dedicated observational effort will undoubtedly provide even more detailed and higher-resolution data for the quantum AI system to analyze, potentially revealing even finer details about Proxima B's surface features, atmospheric dynamics, and overall environment. Looking towards the future, NASA is also actively investing in the development of next-generation quantum AI systems that are specifically optimized for the unique challenges of exoplanet data analysis. According to NASA's current projections and timelines, these enhanced quantum AI systems are expected to become fully operational by early next year. This technological advancement promises to unlock even deeper insights, not only for Proxima B as we continue to unravel its mysteries, but also for the vast catalog of thousands of other exoplanets already in the James Webb Space Telescope's observation queue. Many of these distant worlds, previously deemed less promising or simply too complex to fully understand with traditional methods, may harbor similar hidden secrets just waiting to be uncovered by the power of quantum-enhanced data analysis. The scientific community, while buzzing with excitement, remains cautiously optimistic about these groundbreaking findings. Dr. Jesse Christiansen of NASA's Exoplanet Science Institute perfectly summarizes the prevailing consensus view. While we are absolutely not claiming to have found definitive evidence of life on Proxima B, what we have discovered is a planet with environmental conditions that appear to be far more favorable and dynamic than our previous models predicted. This forces us to significantly expand our understanding of planetary habitability, particularly around the often overlooked red dwarf stars that are actually the most common type of star in our Milky Way galaxy. The profound implications of these discoveries extend far beyond just this one nearby planet. The remarkable success of quantum AI in revealing previously hidden patterns within Webb's data is prompting astronomers to revisit and reevaluate existing datasets collected from other exoplanets by various telescopes over the years. Many worlds that were initially deemed uninteresting or inconclusive based on traditional analysis might now harbor similar tantalizing secrets, just waiting to be unlocked by the application of these advanced analytical methods. This breakthrough in data processing is not just a step forward. It's a fundamental shift in our approach to exoplanet exploration, and it represents just the very beginning of what quantum computing will undoubtedly reveal about the incredible diversity and potential for life throughout our vast universe. Thank you for joining us on this incredible journey of discovery. What do these amazing findings about Proxima B make you wonder about the universe and our place within it? Do you think life might be more common than we currently imagine? Share your thoughts and questions in the comments below. We love hearing from you. Remember to subscribe to our channel and turn on those notifications so you don't miss our next video, where we'll be diving into what this revolutionary quantum AI technology is beginning to uncover about other potentially habitable worlds lurking out there in the cosmos. Stay curious, keep exploring, and from all of us here,